We were discussing the dynamics of a linear dynamical system, 2 by 2 system. We took a very simplified situation where the eigenvectors are orthogonal and they're aligned with the coordinates, so that you can make some simple calculations. We found that there are many different kinds of fixed points that you can have even in a two-dimensional linear dynamical system. So like this, stable node, unstable node, saddle, focus, stable, unstable focus, center, star, and a line of fixed points. Now it can so happen that in some dynamical systems, as you vary some other parameters of the dynamical system, for example, in the two-dimensional system, there's a matrix which defines the dynamical system, the matrix A, which has 4 elements. So you can think of them as parameters. If you vary those parameters, it can so happen the dynamics can changes suddenly at some critical values of parameters. Right? For example, as you vary some parameter, a stable node can become an unstable node, or a stable node can become a stable focus, right? And so on. So, or a stable node can become a center, so that it starts oscillating. So these sudden change in dynamics can take place as you vary some parameters. Such changes are called, sorry, such changes are called bifurcations. So why do you have to study this? The thing is, first of all, we said you can describe a single neuron or a whole brain as a high-dimensional dynamical system. And even at the level of single neuron, bifurcation is very important to study, because even the simplest description of a neuron involves some kind of a bifurcation. Let me give an example. So a little bit of background. Maybe I'll describe this in detail in the following classes. But just in this context, let me just say that a neuron can basically live in 2 states. So this is a neuron, the cell body, and it has an active voltage. So there's a voltage difference between inside and outside, and we call that quantity Vm, which is called membrane potential. And this quantity Vm, right, in a normal neuron, which is in what is called a resting state, this quantity is simply a flat line, typically about minus 70 millivolts. And so this is Vm. It's a flat line. Now, if I inject some current in it, okay, a short pulse, I'll call this Ix, right? So this is Ix. Then what will happen? You will find a small blip in this voltage. It will increase briefly and then come back normal, right? So there is some kind of dynamics going on. What kind of if you think of this as a fixed point, what kind of fixed point is this? Can you guess? So let us say there is Vm is one variable. There are a few other variables in the background which I'm not depicting right now. Now I perturb the system by injecting some current like a pulse. That is, I just kick it off that point, and I'm just seeing what happens. The voltage increases, so this is minus 70. Voltage increases and comes back to the same value. So this kind of a dynamics represents which of these following fixed points? Any guesses?
Stable.
Yeah, stable. It could be stable node or a focus. We'll see that later. But definitely it is stable because it returns to the same state. Now something interesting happens if I inject a slightly large current. Okay, so imagine that my Ix is actually a slow ramp like that. This is time, but it's varying slowly. So what will happen to Vm is interesting. So Vm also will increase a little bit. So this is, let's say, minus 70. It will increase, but suddenly at some point it will start oscillating. Sorry, it's a fixed amplitude. fixed amplitude, fixed the time period, etc., etc., and it will start oscillating. So you see that until this point, it is a fixed point until this value of ix is at this point, let's say some value, right? It is a fixed point, let us say stable node, right? And here it is, I'll just vaguely say oscillations because it's not exactly center. Center is the only one among those that we have described, which gives you oscillations. This dynamics is not exactly center because it's a nonlinear phenomenon, because it has a fixed amplitude and time period. So that anyway, right now I'll just say oscillation. So thing is, as you vary this parameter gradually, continuously, Ix, and slowly, the dynamics suddenly changes qualitatively, right? Uh, so at some critical value of this. So such a phenomenon is called the sudden change in dynamics, right? Just say it. It's called a bifurcation. Sudden change in dynamics as a parameter is varied continuously, right? That's called a bifurcation. So even the basic description of a neuron, right, involves a bifurcation phenomenon. So let us now look at how we can study bifurcations in a two-dimensional linear dynamical system. So let's say we have the same system, x dot equal to ax. Now it's I will consider a two-dimensional system. So A is a 2 by 2 matrix, right? And so given by A, B, C, D. So now let us look at the eigenvalues of this. So take determinant of A minus lambda I, right, and set it to 0. So that gives you this. And if you solve this, you get this equation, lambda square minus tau lambda plus delta is equal to 0, where I'm defining two quantities, tau and delta, which is tau is A plus D, delta is AD minus BC. And usually you can recognize that AD minus BC is the determinant of the matrix, and A plus D is the trace, right, some of the diagonal terms of the matrix. So if you solve for lambda, right, we have lambda 2 is equal to lambda 1 comma lambda 2 is equal to tau plus square root of tau square minus 4 delta by 2. Okay. So now the question we are asking is, as you vary delta and tau, because the eigenvalues depend on delta and tau. So delta and tau are the parameters. As you vary delta and tau, that will vary lambda 1 and lambda 2. And lambda 1 and lambda 2 determine the dynamics. So let us ask the question, how does the dynamics vary as you vary delta and tau? So let's see that. So take the first case, this delta is negative. So that is, so let us look at this delta and tau space. Let us look at this entire part, and delta is negative. So what happens when delta is negative? So tau square, so these are the roots, right? So tau square minus 4 delta is positive. So therefore, first of all, roots are real, right? And this mod of square root of tau square minus uh, 4 delta, because this quantity now is greater than tau in magnitude, right? Because something positive is added to this. So this is greater than mod tau. So therefore, right there, sorry, we are looking at, so this is positive. Yeah, so the roots will be, one will be negative, one is positive, right? So it's a saddle node. Now, if delta is greater than 0, right? So that is tau square minus 4 delta is greater than 0. So delta is greater than 0. So this is negative. This whole thing is negative. So tau square minus 4 delta can be positive or negative. So now let us take a subcase of tau square minus 4 delta being positive. It is positive, but this quantity, right, the magnitude of this is less than tau or this thing. So therefore, if tau is positive, both roots are positive. So this is less than this. So so tau is greater than this. So tau plus this gives you a quantity that is positive. Tau minus this also will be positive if tau is positive. Therefore, both roots are positive. Similarly, if tau is negative, right, again this dominates this term, so both roots are negative. So if delta is positive and if tau square minus 4 delta is positive and if tau is positive, then you have the case where roots are positive and you have unstable nodes. And if tau is negative, then both roots are negative, you have stable nodes. So then, so we have taken this case before, tau square minus 4 delta is positive. So when tau square minus 4 delta is negative, then what happens if this is negative, the roots are complex. So roots will be tau plus plus or minus I times something. So now if tau is positive, real part is positive, that's an unstable focus. So tau is negative, the real part is negative, so that's a stable focus. So finally, if tau is 0 and delta is positive. Okay, so tau is 0, delta is positive means what? So it is 0 plus or minus I times 4 delta. Okay, so lambda 1, lambda 2 is equal to this. So which means it's purely, both are purely imaginary, so that gives you a center. So then if delta is 0, then it is delta is 0 means lambda 1 lambda 2 is equal to tau plus tau and tau minus tau. So this is 0. Okay, so one of the roots is 0. If one of the roots is 0, what do you have? We have seen it yesterday. It's a line of attractors, a line of fixed points. Then finally, the last case is tau square minus 4 delta is equal to 0. So that means this term is 0. So then lambda 1, lambda 2 are both equal to tau. So both roots are the same. So if both roots are the same, both eigenvalues are the same, then you have a star. That is the flow lines are all straight lines and everything points either into the fixed point or out of the fixed point. But so if tau is positive, everything flows outside. Tau is negative, everything flows inside. So let us put these all together and summarize them in one picture, or we call it a map. It's a bifurcation map, right? So if first thing is tau is negative, it is an easy case. If tau is negative, you have saddle nodes. So this entire thing on the left side, right, it's just saddle node. So there's nothing else matters. If delta is negative, you have only saddles, so nothing else matters. Now for delta positive, uh, if tau square minus 4 delta is greater than 0, right, and then you have unstable nodes, and tau is positive, unstable nodes. Unstable nodes, this part. Similarly, if tau is negative for the same condition, you have stable nodes. Now, if tau square minus 4 delta is less than 0, then you have complex roots or complex eigenvalues. Then if tau is positive, you have a stable focus, that is this, or stable spiral. The focus is also called a spiral, right? Spiral and is same as focus. All right, and similarly when tau is negative, you have stable spiral. Okay, so on the right side, if tau is positive, you have unstable. If tau is negative, you have stable. But within these two quadrants, there's again the subdivision, which is divided by the line of delta square minus 4 delta equal to 0. If this delta square minus 4 delta is positive, right, you get nodes. Okay, and if it is negative, you get spirals. So this is a broad architecture of this map. Now let us look at even further what happens on the borders. Right, on the borders, you have again three borders. Uh, delta equal to 0. What is that? So that is this vertical line. That is y-axis. That is a tau axis. And on the tau axis, what did we get? the line of fixed points. So this is the line of fixed points or non-isolated fixed points. What that means, the same thing. What that means is normally a fixed point is just a single point. Okay, when you talk about a fixed point, it's a single point, right? And there's nothing else nearby. There's no other fixed point within some epsilon distance. But whereas in line of attractor, there's a continuous line which is all fixed points. So that is therefore it's also called non-isolated fixed point. So that is what happens on the tau axis. That is when delta equal to 0. Now when tau equal to 0, delta is positive, right? You get centers. You get another border. The third border is when delta square minus 4 delta is equal to 0. So you have seen that. And two roots are the same, that is star. Okay, so like that, you see that even in a simple 2D system, which is linear, you have a wide variety of dynamics happening and wide variety of fixed points. And as you vary these parameters, as you move around in this parameter space, in this delta tau space, so suppose you start from this somewhere in this region, you slowly increase your delta, right? Then you cross over to the unstable node region, or you are in the lower part, increase your delta, you cross over to stable node region. Or from here you move further up like this. You cross over into the stable spiral region. Stable node becomes stable spiral. Or you move further up north, right? A stable spiral becomes unstable spiral. Until then, it will be attracting. Or suddenly, once you cross this line, it will start repelling. So, like that, as you vary some parameters, the system changes its dynamics, and you see such its dynamics in a simple case. So, let me take an example. Interesting example. I thought you might like it. This is given in Stogart's textbook. So, by the way, all this dynamical systems stuff for this, I'm using Stogart's book as a reference. I think I mentioned that in the very first class. This is dynamics of interaction between this girl and this guy called Romeo and a girl called Juliet. So the problem statement is like this: Romeo is in love with Juliet, but in our version of the story, Juliet is a fickle lover. The more Romeo loves her, the more Juliet wants to run away and hide. And when Romeo gets discouraged and backs off, Juliet begins to find him strangely attractive. So Romeo, on the other hand, Romeo is a very simplistic guy, right? Juliet is more complicated, but Romeo is pretty straightforward. Romeo, on the other hand, tends to echo her. He warms up when she loves him, and he grows cold when she hates him. So it's very simple. So how will you describe their fate? How do you describe their romantic dynamics? It's something like this. Let's say you have take two variables R and J. R represents Romeo's state of mind, emotional state. J represents Juliet's state of emotional state. Right, at a given time t. So now, how do you describe the interactions? R is simply response, co-evolves, changes in the same way, echoes Juliet's emotional state. So R dot is equal to AJ. Okay, if J increases, R also increases. J is positive, that is positively, favorably disposed. R also increases, and both A and B are positive. So J dot is equal. J's changes are opposite. If R is positive, J gets put off, and if R is negative, J gets interested. So J dot is equal to minus BR, and both A and B are positive. So if you write down the equation, so like in this of the form x dot equal to Ax, and A is given by 0, A, B, minus B, and 0. So if you find the eigenvalues, it will be lambda equal to plus or minus I times square root of AB. So both are complex, both are purely imaginary. So therefore you have center. So they keep oscillating. So they'll never stabilize. Ideally you want both to be in the positive state and they're happily married and all that. But that will never happen. They keep chasing each other. It's a never-ending saga of love and hate. So it's just a funny example how you can formulate even social dynamics in a mathematical form, arrive at some insights. Okay, so all that is just about very simple system, simplest system possible, simplest non-trivial system possible, which is a two-dimensional linear dynamical system, right? In an n-dimensional system, it is slightly more elaborate, but the theory is slightly straightforward. But things start getting messy when you have a lot of eigenvalues which are zero, and it's non-singular, and you have singular matrices, and all that becomes a bit tricky. But otherwise, it's simple. I mean, you have if you have all lambdas positive, it's unstable. All lambdas negative, it is stable, and or the negative real part also. And if there is some positive lambda, some negative lambda, it's a saddle node, and so on and so forth. Okay, so linear system, even in dimensions, if it is non-singular matrix, it's somewhat straightforward. Now let us go to a nonlinear system, right? But a two-dimensional system, because a nonlinear two-dimensional system is somewhat tractable. You can analyze it, you can do a lot of analysis on that, understand how it works, especially if it is a continuous system. So nonlinear system in high dimensions is very hard. Theory is very hard. There's no general theory, so we won't touch that in this course. So we'll spend some time on discussing the nonlinear two-dimensional systems because a lot of single neuron models, popular single neuron models, are two variable systems or two-dimensional nonlinear systems. So let us spend some time on that. So the way you analyze such two-dimensional systems is called phase plane analysis, because you describe the dynamics, because it's a two-dimensional system, right? You describe dynamics on a plane consisting of x1 and x2. So such a plane is called the phase plane. And since it's two dimensions, you can draw pictures, you can do a nice pictorial analysis. So therefore, that kind of analysis is called phase plane analysis. Okay, so let us describe such systems. The advantage of describing two-dimensional systems or handling two-dimensional systems is I can easily be visualized because I can draw the pictures on a plane. And 2D also is already quite rich, can have very rich dynamics, can be very complex, and it's sufficiently interesting. They show, for example, something that cannot be seen in a two-dimensional linear system, that can be seen in a two-dimensional nonlinear system, which is called a limit cycle. Okay, so that is a periodic behavior. So in case of a center, that's also periodic, but the amplitude depends on initial condition. Right, so this is a center. Whereas in case of limit cycle, amplitude doesn't depend on initial condition. It kind of always goes to that particular loop. You start from inside, it will expand and go there. You start from outside, it will contract and go there. Okay, so it will always go to that loop. And that kind of dynamics is what you need to describe these fixed amplitude oscillations of a neuron. Okay, so limit cycles are quite important, and they can be exhibited already in a two-dimensional nonlinear system. So that's important for us. But a two-dimensional system obviously have a limited range of dynamics compared to n-dimensional systems. We'll also simulate n-dimensional systems, but they're very hard to analyze theoretically. So we'll just satisfy ourselves with simulations. Okay. So how do you describe a general two-dimensional dynamical system, right? So it's a two variables, so we call it x and y. So x dot is equal to some function f of x, y. So earlier we had linear system f of x comma y was simply something like ax plus by. Okay, but now that's not the case. So x dot is equal to some nonlinear function f of x comma y dot is equal to another nonlinear function g, which is g of x comma y. So how do you analyze this? The very first thing that you do is to identify all the fixed points and classify each of them by local analysis. Now, how do you find fixed points? Now, what are fixed points? So fixed points are the points where x dot is equal to 0 is equal to y dot, where the flow is 0, right? So x dot equal to 0, y dot equal to 0. How do you do that? So since x dot is equal to f of x comma y, which is 0, y dot is equal to g of x comma, which is 0. So we are looking at the intersection points of these two curves. F of x comma y is 0, is a curve. G of x comma y equal to 0 is also a curve. Right now, if you look at their intersection points, they are the fixed point because that's where both x dot and y dot are 0. So these curves, those intersection points we are seeking, they are called null lines. And the first equation, which is f of x comma y equal to 0, that represents what is called an x null line because that's where x dot becomes 0. And the second equation, g of x comma y equal to 0, is called the y null line because that's where y dot is 0. So therefore, the intersection point of these two null lines are the fixed points of the system. So just a simple illustration. So this is my xy plane. So x-axis and y-axis. Um, let's imagine that this curve, right, is the f of x comma y equal to 0 curve, right? So that is the x null plane. And this other curve, which is g of x comma y equal to 0 curve, that's the y null plane. So what are the fixed points now? The intersection points of these two curves. So that is this and this. So there are two fixed points. What is the objective of our study of this dynamical system? That is, in case of a linear dynamical system, right? We determine the fixed point, which is origin. What we did is we want actually ideally we want to understand the flow of the system everywhere in the plane or everywhere in the state space. In two-dimensional linear system, we determined that. So we know how the flow will be in every quadrant. And so whether the flow is towards the fixed point, away from the fixed point, or partly towards, partly away, does it go straight towards the fixed point or does it spiral towards fixed point? All those things we have described. So although we start with the fixed point, with the fixed point as a starting point, we were able to describe the flow of the system over the entire plane. That's what we have done in the previous case of the linear dynamical system, linear two-dimensional dynamical system. Similarly, even in case of a nonlinear dynamical system, we want to understand the flow of the system everywhere in the plane. So you can write a program and do it, but that's not very interesting. How do you theoretically, analytically find the flow, right, of the system everywhere in the state space? Here you call it the phase plane or the xy plane. So finding the fixed point is a crucial part of this analysis. So how do you do that? You define x and y in terms of new variables, epsilon x and epsilon y. So let us say this is kind of fixed point. Okay, and at that point I'll call it x naught and y naught. So just like before, we had origin and we studied dynamics around the origin. So now we don't have origin, we have this fixed point. We want to study dynamics around this fixed point. What happens? Is it stable? Is it unstable? Will this flow go towards it, away from it? All those things. So you define this new variable epsilon x as this. So therefore, x equal to x naught plus epsilon x, and x naught is equal to x naught is constant. So x naught is equal to simply epsilon x dot. Okay, so if you plug this into the original equation, x dot is equal to f of x comma y, right? If you plug this in here, what do you get? Epsilon x dot, right, is equal to f of, you expand this in a Taylor series form. This is a Taylor series of a two-dimensional function. You must have done Taylor series of a 1D function in your JE days, but hopefully you must have done 2D also sometime in your other courses. So it is f of x naught y comma y naught plus the linear terms in terms of epsilon x, and because you have two variables here, just as y x equal to x naught plus epsilon x, y is equal to y naught plus epsilon y. So therefore you have the linear terms here, epsilon x into dou f by dou x plus epsilon y into dou f by dou y plus higher order terms. Similarly, for the other equation, you have epsilon y dot is equal to g of x naught y naught plus epsilon x times dou g by dou x plus epsilon y times dou g by dou y plus higher order terms. So now we'll ignore these higher order terms, right? Ignore them, and you get a linearized version. So I'm only looking at dynamics in a small neighborhood, which can be where the system can be approximated by a linear system. All right. So that will be this epsilon x dot epsilon y dot is equal to this matrix J. By the way, this kind of a matrix is called a Jacobian, right? Which we obtain by differentiating f and g. So f and g are functions of x and y. So you differentiate f and g with both the variables, and you get a matrix that is called a Jacobian. So the linear approximation of the above nonlinear system, right? This nonlinear system in the neighborhood of the fixed point x naught y naught is given by this equation. And once you have it, therefore you have epsilon dot is equal to j epsilon. So this is the approximation. So the fixed point now is at epsilon equal to 0, just like the previous case where fixed point is at x equal to 0. Here we have fixed point at epsilon equal to 0. So now we need to analyze this. So what happens? So what we'll do is let's take a small example, right, and see how it works. The two equations are x dot is equal to minus x plus x cube, and y dot is equal to 2y, right? And so how do you find the fixed points of this? Okay, so f of x comma y is equal to minus x plus x cube, so that is equal to 0, right? And so what are the null lines? Can anybody explain? Hello. Sorry.
Those are the curves at which x and y are 0. It's not like
See, normally in the previous general example, the external line we have taken to be this, right? So it's a curve. F of x y equal to 0 gives you a curve. But here, f of x comma y is equal to minus x plus x cube. There is no y at all in this expression. And now you solve for this. Okay, if you solve for this, what do you get? Minus x plus x cube is x into minus 1 plus x square is equal to 0. What is x? Minus 1, 0, 1. How is this the null line? What's going on? Null line is
Y-axis
supposed
and
to
two
be
lines parallel to it.
huh?
Y-axis and two lines parallel to it.
Yeah, very good. Right. So x equal to minus 1, 0, or 1, y equal to anything. Okay, so the null lines are these three parallel lines. Yeah. Yeah, please mute yourself if you are not speaking. Right, so that is three null lines. The three parallel lines form the null x null lines, right? So it is a slightly strange example. So similarly, for the second equation, it is dy by dt. Basically, the two variables are decoupled. That's why it looks slightly weird like this. So y dot is equal to minus 2y. So that is g of x 1 y equal to minus 2y, which is equal to 0. Y is 0. So y is 0, x is anything. Okay, so that is the entire x-axis. Okay, so the external lines are three parallel lines. All three are vertical, right? And y null line is the x-axis. Now, what are the fixed points now? What are the fixed points? So basically, it is like this. So this is y null line. All these three are x null lines. Okay, where are the fixed points?
1 comma 0, 0 comma
Yes.
0, and minus 1 comma
Very
0.
good. So the fixed points are these 3 points. So the fixed points are minus 1, 0, 0, 0, and 1, 0. So given by this 3. Okay, so it's like this. So what we are doing here is, it's like, let's say we take the IIT campus. right? You want to give directions for somebody coming from outside to some hostel, say Narmada hostel, right? You just say that, what will be the directions, like, you enter the in gate, come to the first fork, right? Then take the left branch of the at the fork and keep going, right? And then you'll find another big junction. It's called shopping center. Keep going straight. Another big junction called Rajendra Circle. Take a left, right? So your directions will be mostly in terms of the junctions. You won't give the detailed trajectory and what at what angle you have to bend and all that, because road keeps bending. You don't have to give the details about every bend in the curve. You only give details at the junction point, which is where some transitions have to be made. So similarly, if you want to understand the flow over the entire phase plane, the fixed points are crucial. These are like your junctions when you give directions, right? So you because and that's where the flow stops. Flow becomes zero. So you understand the fixed points, determine the fixed points first, then determine the flow around the fixed points. Right after that, you just extrapolate that and find the flow everywhere. So these are the kind of 3 steps in understanding the dynamics on the phase plane. So you got 3 fixed points, right? How do you find what kind of fixed points they are? So for each of them, basically you have to construct an equation like this, right? Because you have to look at the fixed point, find the Jacobian, find the linear version of it. Then how do you find stability? Anybody? Once you find linear expression, yeah,
Eigenvalues
of
uh, the Jacobian.
very good. Eigenvalues of Jacobian. You find eigenvalues of the Jacobian, right? If there are any positive eigenvalues, or even if they're complex, if they have positive real parts, then it is unstable, right? So like that, you classify the fixed point and you get the flow around the fixed point, and then you can extrapolate that. So let us see how that is done. So first, let us find the Jacobian. Jacobian is dou x dot by dou x, dou x dot by dou y dot by dou x, dou y dot by dou y. Okay, so that will be, if you look at this expression, minus 1 plus 3x square, right, and 0, because x dot depends only on x and y dot depends only on y. So it's a very simple system. So this is a Jacobian. And now let us calculate the Jacobian at the 3 fixed points. Right, at 0, 0, it is, if you plug it in, you get minus 1, 0, 0, minus 1. And you can trivially see that the roots are lambda 1, lambda 2 is equal to minus 1, minus 2. It's a stable node, right? And at plus or minus 1 and 0, since it depends on x square, so it doesn't matter whether the root is plus 1 or minus 1. So you get 2, 0, 0, minus 2. So the eigenvalues are 2 and minus 2. So they are saddle nodes. Right. So from this, what we can find out is that the fixed point at the origin, okay, that is a stable node, and the fixed points at these two were other ones, minus 1, 0, and 1, 0, both are saddles. So now let us try to figure out what is the flow around this. So this is a stable fixed point, so flow goes towards it in all directions. So flow goes towards it in all directions, including x direction and the y direction. So these two are saddles, right? Flow goes around it in a slightly weird way. In one dimension, it goes away. In one other dimension, it goes towards. Right. So obviously, on this axis, you can see that flow has to be going in this direction, because at this point, flow is going in this direction towards the left. Therefore, here also flow must be going away from it. So if flow goes away from it in this direction, opposite side also should be going away from it. So if it goes away from it in the x direction, it should be going towards it in the y direction. I'm simplifying the arguments because we'll have to make a more precise, rigorous thing. We'll have to cover more ground. So let us live with this for now. That's why I've taken deliberately a very simple system where x and y are totally decoupled, so that your eigenvectors are aligned with the x and y axis. Okay, so this is saddle node where on the x direction it is unstable, y direction it is stable. So similarly, you can apply similar arguments and say that since on the positive side flow is towards the origin, right, then at the fixed point given by 1, 0, the flow must be away from it in the x direction, right, and flow must be towards it in the y direction. Okay, so now if you extrapolate this, you can kind of start guessing how the flow will be in all over the place, all over the phase plane. So let's take this fixed point again, this stable node, which is the origin. So flow is towards it in all directions. So if you are here, you might go like this, right? Okay, which is consistent with what we found in the neighborhood. Then what about this fellow, right? Since the flow on the right side, right, is going to, so at any given point, the x direction, if you are in this quadrant, for example, near the fixed point, I'll call this fixed point fixed point number 1, this fixed point number 2, fixed point number 3. At fixed point number 1, if you are, with respect to it in the top right corner or top right quadrant, right, you must be flowing downwards and rightwards, right? So therefore, it looks something like this. And similarly, if you are in the bottom right quadrant, you must be flowing upwards and rightwards. So something like that. If you are in the bottom left quadrant, you must be flowing upwards and leftwards. So it is like that. So if you are in the top left quadrant, you must be flowing downwards and leftwards. So the flow around the saddle is like that everywhere. And you can extrapolate that and imagine what the flow will be like slightly farther away from the fixed point. Similarly, if you take the fixed point number 3, right, let's say look at the top right quadrant. Flow here is downward and rightward, so it will be something like that. Bottom right quadrant, flow is upward and rightward. Bottom left quadrant, flow is upward and leftward. Right, top left quadrant, flow is downward and leftward. Okay, so like that we are able to reconstruct the phase portrait, right, over the entire phase plane. So how did we do that? We took it in 3 steps. First, identify the fixed points, right? Then examine the dynamics in the neighborhood of the fixed points. How to do that? Linearize the system around the fixed points, calculate the Jacobian, study stability, find out what kind of, not only just stability, find out what kind of stable point it is, what kind of fixed point it is, right? And using that, you can draw the phase portrait in the neighborhood of the fixed point. And after that, you can draw some pictures and extrapolate and find out what's happening over the entire plane. Okay, so you can, so what we'll do in the next class. So, okay, Friday's class is not there because it's a public holiday. You can take up some simple examples like this, right, and try out, doing phase plane analysis by yourselves. In Monday's class, I'll take the regular class, but Tuesday, what we'll do, Sandeep will take a tutorial. There's some nice software tools which will let you examine, do the phase plane analysis given a system. You can plug in the equation and you can draw the null lines and vary some parameters in the equation, see how the null lines change, how the fixed points change, and all that. So a very nice, fun exercise. Using such a software tool, you can examine systems like this. Okay, so even for a two-dimensional system, you can get very fancy dynamics like this. It looks like an octopus or whatever. So that's all. Thank you. If you have any questions,